All right, so this lesson is about integration by trigonometric substitution. So we've talked about integration techniques before. We've talked about u-substitution, right? A long time ago. We did integration by parts using the DI method. That was one of the shortcuts that we used there. We just got finished integrating by partial fractions, using partial fractions. Now we're going to do another technique of integration. It's called trigonometric substitution. So we are going to be substituting, we are going to be using trig ratios, and these are this is sort of what it looks like when you want to consider this. And again, later, next week, probably early next week, or maybe even tomorrow, I'll give you a sheet, a summary of sort of what to look for and how to choose the right integration technique. But this one, what we're focusing on here is we're focusing on a square root with some kind of constant, plus or minus an x, or an x squared term here, plus or minus some kind of constant, okay? So we have the square root of ax squared minus x squared. Now, every constant number is a square, right? Some are perfect squares, like 16 and 4 and 9, and some are not, like 3 and 5. But there always is a square root, which we'll do examples later where we'll do this with numbers that aren't perfect squares. So any of these right here that you see will be good candidates for trigonometric substitution. All right, so the big question is, in this introduction, is why trigonometric substitution? Okay, integrating a radical with an expression underneath is nasty. It's not easy to do. So if we can get rid of the radical and try and get it down to some kind of expression without a root sign, that's going to give us a better chance. So for integrals in these forms, substituting trigonometric functions allows us to eliminate those radicals. So I just want to give you a little quick verification on this idea. So let's take a look at something like this. Okay, if I had the square root of 1 minus x squared. Do you see how this is a pattern of our first example right here? Okay. Excuse me. So if we had this right here, and you're saying, okay, we got a radical there, but I'd like to get rid of that radical. I want you to recall the fact that sine squared theta plus cos squared theta equals what? Remember this? 1. Yeah, equals 1. Now if I rearrange some things, and I've got cos squared theta equals 1 minus sine squared theta, or even better, cos theta equals the square root of 1 minus sine squared theta, what happens is we start to see this is very, very familiar to this right here, isn't it? It's very, very similar. Very, very similar. And the neat thing about this is that this over here is equal to a trig function that doesn't have a radical anymore. Okay? So we can actually move from a radical with an expression underneath to a non-radical. The key is using trig functions. So again, this is really important, noticing this. 1 minus sine squared theta, this is the pattern that we kind of see there. If we substitute in sine squared theta, so let's sub x equals sine theta. Let's just do sine theta. So this is now the square root of 1 minus sine theta squared. That's actually equal to 1 minus sine squared theta, which is equal to the root of cos squared theta, which is cos theta. Okay? You with me so far? So again, we went from here, radical, expression x, to no radical, and trig function. Okay? So this is the key. This is the basis for why trig substitution is going to be helpful to us. Because this is tricky to integrate. This, very easy to integrate, right? Okay? Now there are obviously more complicated versions of this. There are variations. I mean, for example, like what happens if a is not 1, or if a is not a perfect square? Well, obviously if a is not 1, we've got other issues. So we'll talk about that in a second. But just a quick note on this. So again, the reasons why this is great. There's two things why this is great. Okay, so this format is now in terms of theta. I guess this isn't a great part, but this is just a note, okay? So a note here. The format is in terms of theta, okay? Not x. So we have to be aware of that. And later, we will turn this back to x, because again, the question was, what is the integral of this expression dx? So if we've moved this now to theta, or cos of whatever, we have to take it back there. Okay? So that's the first note. Okay? Formatting here. All right, the second note is that this works for numbers other than 1 too, because 1 is in your identity, but this works for other numbers as well. Okay? So before I get to this handy little chart, I'm going to do a quick example here with, let's go back to this again. So root a squared minus x squared. If we have this, and let's say that a is some other number, all we have to do is we have to substitute, instead of subbing x equals sine theta, we sub x equals a sine theta. Okay? And I'll show you what this turns out to be and why this works. And notice that this is the format with a squared. So that a is going to be the square root of whatever number this is. So first of all, I'll do it with a just intact there so you can kind of see. So we have a squared minus now a sine theta all squared, which this is a squared minus a squared sine squared. Did you need something? Yeah. Simplifying that further, we have a squared. If we can take that out, that's now a 1 minus sine squared. Okay? So now we're kind of back to our Pythagorean identity. The only thing is we have this a going on here. Well, really the square root of a squared is a. So we kind of have this, right? Which 1 minus sine squared theta is cos squared theta, the square root of that. This turns out to be, just to save some space here, turns out to be a cos theta. Okay? So if a is other than 1, that's no problem. We can substitute in the square root of sort of this constant that we see under the root sign, that is a, and we're going to get a cos theta. So we're still going to be able to get rid of the radical sign, still going to write this in terms of a trig function. It's going to be easier to integrate. Okay? So I will now get to this little chart here. So these, remember these original integrals I showed you up here? So these are the forms. You're going to look for these kind of things. So I'll get you to take a moment to write this down. Again, this is the first one that we used, a squared, the square root of a squared minus x squared. We're going to substitute a sine theta in for x. That's going to allow us to manipulate that expression and get rid of the radical. All right, so I'm going to bring these integrals back into play here. So notice something, and I'm just going to show you this now, because when we're going to get into this, the whole switching from x to theta, so in terms of x to in terms of theta, if we're going to do the integrating, and let's just say that this a squared minus x squared, right, this is going to go to some trig function like, it's going to end up to be a cos, but it's going to be in terms of theta, isn't it? So if we want to actually do this integration with a simpler integrand, it's going to be in terms of theta. So guess what? This also has to be in terms of theta. More specifically, it has to be d theta. Okay, so with respect to theta. And what that means is that in here, of course, we have this a sine theta. We are going to also have to find out what dx is, okay? Which is no big deal, right? I mean, dx is a cos theta d theta. So we want to keep this in mind, that the dx is going to turn into d theta because we take the derivative of x with respect to theta. So I just kind of wanted to outline that. So for example, again, x is going to be a tan theta, and dx is going to be a secant squared theta d theta. Right? So we're going to need that later. And when we take x equaling a secant theta, you might want to get this. You might want to get this integral, derivative paper out, right? You might want to have that handy because you might need to take some integrals of some things you haven't got memorized. But secant theta, does anybody remember offhand what secant theta is? Probably not. You haven't looked at that really ever. So dx, that's going to be a secant theta tan theta, I believe. Secant theta tan theta, yeah. And then d theta. Okay. So we think about this, and this is going to end up into some function theta. Then we're also going to have d theta with this attached to it, right? So you're going to have a secant theta tan theta multiplied, right, by whatever you have here and the d theta. So yeah, we're going to be able to integrate in terms of theta. Now we'll do some examples where we do just that. So we're going to take this, again, let's go back to the beginning here and just think about what we've done so far. Okay? We're going to take these radical integrands, we're going to do some trig substitution if they're in these forms here, and we're going to rewrite that integral as some kind of trig function d in terms of theta, d theta. We're going to then do the integrating, and then we're going to have to move it back to terms of x. Okay, so that's kind of the next step, and that's not too bad. It's a bit of a rabbit trail at times, but you know, that's sort of the overall, the big picture process. Okay, so are you guys ready for an example? You guys ready for an example? Okay, so let's do an example of, here's example 1. Let's do this one, I'll do it in blue. So let's take the integral of 4 minus x squared all to the 1/2 dx. All right, and of course, if you have something to the power of 1/2, that is the exact same as the square root of 4 minus x squared, right? Now this follows the pattern, one of the patterns that we see, right? This is the example that we did. We have a squared minus x squared. That's the pattern, the square root of a squared minus x squared. So we're going to be substituting tan. Remember, this 4 is actually 2 squared, right? So think about this as 2 squared minus x squared dx. So our a is going to be 2. All right. So if that's the case, then what we want to do is we want to sub in for x. We want to do the square root of 4, which is 2 sine theta. Okay? 2 sine theta. Now we want to find out what d of x is in terms of theta as well. So you may as well just do them right together. I always do them right together here. So it's just 2 cos theta d theta. All right. So you kind of have that just in your pocket. So let's go back over here. I'm going to change colors here now, and we're going to do this. We're going to do the integral of. Okay. So we're going to have. Really, you can write this as 2 squared if you want, or 4. I'm just going to write it as 4. Minus, now x is going to be 2 sine theta. And that's going to be all squared with respect to x. Everyone see that? X equals a sine theta, or 2 sine theta. So now let's do some simplification in here. All right, so this is actually square root of 4 minus 4 sine squared theta. And you guys are quick as whips already. You're already seeing that we're going to be able to see a 1 minus sine squared in here, right? So we pull a 4 out, and I'm left with 1 minus sine squared theta. Oops, bracket. Okay, so this is good. This is good. Square root, okay, well, let's just carry this through. So that's going to be 4 cos squared theta, correct? Now, as you see how I have theta and x here, these last few steps? That's kind of bad. That's kind of bad, isn't it? So what do I need to do? I really should be writing this in terms of theta, right? Because I can't integrate yet. So anytime throughout this process, and you could do it right at the beginning so you don't have a theta and a dx, it looks dumb. So anytime we should be replacing this dx with this right here. So let's do that now. I'm going to do that now because I don't like the looks of that. So I'm just going to do it in this step, and then we'll keep going. But dx is actually 2 cos theta d theta. So times, and you can rewrite that or just erase the guy off or whatever. But let's kind of get this in our heads that in order to integrate, everything needs to be in terms of theta here. All right? So the square root of 4 cos squared theta is actually 2 cos theta. And I have to multiply that again by 2 cos theta d theta. All right? Everybody with me here so far? So simplifying this again, we have 4, and you can bring that 4 out front if you want. Maybe I will do that now just to save some lines of space here. That 2 times 2 is 4. It's a constant. Bring it out. Now this is going to be cos squared theta d theta. Okay. All right. Now that looks a little bit better than the square root of 4 minus x squared. However, we know the integral of cos pretty easy, but cos squared you might not know. You're probably going to have to learn a few more integrals here, and you have your sheet. Okay. So again, there is an integral for this, a stated integral on your sheet there. So you want to look at that. Sure. Okay. Now there is something called a reduction formula, but again, I think it's probably more complicated to remember that. So for example, if you have cos to the n theta, then there's a formula. You can plug it all in and get what the integral is. But I think let's just memorize cos squared and sine squared and a few of those. So do you see that? What's the integral of cos squared theta? The integral of cos squared theta is actually 1/2 cos x sine x plus x. Okay? That's d theta, of course. And then plus c, of course. So this is what we want to focus on. Do you guys find your sheet there? Ish? Okay. Probably not, no. I have to hand copy it, sorry. All, 36 of them. See what I can find. If you can't find yours, I might be able to find an extra one. All right. So, okay. So, again, this isn't that hard to remember, but the nice thing is that we do have a form for this. So this is actually going to be 4 times 1/2 cos x sine x plus 1/2 x. I'm just distributing this 1/2 in there so I don't have too many things going on here. Okay. Now, that's fine here. 4 times 1/2 here. This is actually going to be then equal to 2 cos x sine x plus 2x. Okay. Oh, wait. I just flipped over to x. That is bad of me. This is theta still, guys. That's definitely not x because, oh wow, big blunder there. Okay, I'm reading off my sheet and it's all in x, but really this is theta, right? Because it's cos theta, so this is theta, this is theta. Yeah, everything's in theta here so far. We are now coming to the point where we have to bring it back to x. So this is plus c, but that's okay. We're going to remember that that's there a little bit later. Okay, so we've come through some of the big steps. We just have this final push now to get this not in terms of theta, but in terms of x. Okay, so here's where we're going to start. Okay, here's where we're going to start. We let x equal what early on? 2 sine theta for this question. So if x equals 2 sine theta, and I'm going to do this in a bit of a different color right up here. Okay, if x equals 2 sine theta, then I can actually solve for theta here, and it will be in terms of x. So I'm going to have x over 2, right, equals sine theta. And how do you get theta by itself if you have it in a sine function? It's like inverse sine or arc sine. Remember arc sine? So I like using arc sine. So theta is going to be arc sine of x over 2. Okay. Okay, so that gets us, that helps us when we have theta and we have sine. So sine of arc sine of x over 2. That's going to be pretty easy. But cos of arc sine. Okay. This is where you can get all the trig functions now from a diagram of a right triangle, because remember the Pythagoras identity comes from the relationship between sine and cos and the right triangle. And theta has a value for sine, cos, tan, depending on the values of the sides of the right triangle, right? So this is going to be great for sine because, like I said, the sine of arc sine of x over 2 is just x over 2. But what do you do for cos? This is what you do. You go to a right triangle. Okay? Go to a right triangle. And what do we know about the right triangle? Well, let's not go here right away. Let's go back to here. Let's say this is theta. This is our right angle. The sine of theta is x over 2. Sine, if you remember SOHCAHTOA? That's opposite divided by hypotenuse. So guess what? I have an x here, opposite, and 2 is going to be my hypotenuse, isn't it? Are we good with that so far? Opposite of hypotenuse. So can we find out what this side is? Because remember, theta, or cos of theta, which is what we need over here, we need cos of theta in terms of x, is going to be the adjacent side divided by hypotenuse. So how do I find the adjacent side? I can go back to Pythagoras' theorem. This squared plus this squared equals 2 squared. Or this right here equals the square root of 4 minus x squared. Kind of handy, isn't it, that we have, that was in our original question, I think. But is there, you see that though? Do you see kind of how you can get those? So again, Pythagoras' theorem, a squared plus b squared equals c squared. Or, this equals the square root, this side equals the square root of this squared minus this squared. Okay? So now we can find out, now we know that cos, right here, cos of theta is the adjacent side, which is now this 4 minus x squared, over the hypotenuse. That's what cosine is. So I have sine theta, which you don't even really need to solve for theta down here. We have sine thetas right here. And now I have cos theta. It's right here. And I didn't fill in my theta here. Sorry, from before when I erased the x. So we will need the theta, but we have sine theta, we have cos theta, and we have theta. Okay? So we will need this theta here. We wouldn't need it for the triangle, but we will need it for substituting in our equation. All right? So theta is right here. So here is sine of theta, here is theta itself, and here is cos of theta. Now I can rewrite all of these things, okay, in terms of x, which was our final push here. So we read that down here. That's going to be 2. Okay, cos theta is going to be the square root of 4 minus x squared all over 2 times sine theta, which was x over 2, right? Plus 2 theta, which we said was arc sine of x over 2. plus c. Doing another level of simplification here, I have 2 over, let's see, I have 2 over 4 here, right? So that's going to be 1 over 2 of this root x, 4 minus x squared times x. So I can just put it, you can put an x over 2, 1/2 times x if you want, or just an x over 2. Might be easiest. So that's what we get here. And then plus our 2 arc sine of x over 2 plus c. So that's what this integral is going to be equaling here. All right, so it's a bit of a process, a bit of a lengthy process for sure. But once you kind of do 5 or 10 of these, it'll start to get a little bit quicker. All right, so that's the introduction to trig substitution with an example there, and we're going to do some more examples here in a bit.